once again, ladies and gentlemen. This is a follow-up of our first topic, which was on functions. If you may recall, I defined a function as a mathematical relationship between variables. And usually in a function, we have two types of variables, the dependent and the independent variable. So we stopped at the illustration of the construction of linear functions in our last lecture. And I'd given an example that time. I'll give yet another example in way of questions in the construction of a linear function. Now, what do I mean by construction of a linear function? Recall that a linear function has a following general form, where y is the dependent variable, x the independent variable. Now when you talk of constructing a linear function, then this simply means we fix the values of a and b so that we have a specific relationship between the variables y and x. So we did an example in form of a question last time. We're going to do yet another example in the form of a question so that we are able to know or get to know how to fix a and b so that you have a mathematical relationship between y and x. So I'll design another question as an example towards that end. So I'll call it question number 2 in the construction of a linear function. Determine the linear equation. The linear equation that passes through the points 1 Roman x comma y is equal to minus 8 and 4, and the second point x comma y is equal to possibly 5 and even 10. So I want to find the linear equation that will go through those 2 points. Remember, we are trying to fix a and b. And if you recall backwards on the properties of linear functions, the property number 3 or thereabout states that to define a linear function, you need 2 points, or a linear function is completely defined once 2 points are given. That in essence enables us to formulate 2 equations which we then solve simultaneously for the constants a and b. So solution to the equation I've just put on the board will take the form. Now recall that that's a general format of a linear function. We have 2 points in the x, y coordinate system. So the first point simply says that when x is negative 8, y is 8. Y is 4, beg your pardon. At that point, this expression becomes 4 for y is equal to a plus minus 8, or rather b, times minus negative 8. That then means this will be the same as a minus, this is supposed to be 8, not 18, negative 8. So this will be 8, negative 8b. The second point, when x is 5, y is 10, the above expression becomes y for 10, a plus 5b. We then solve this simultaneously for a and b, like as follows. Now, by elimination, we can get rid of a. So subtract equation 1 minus equation 2, we have a negative 6 there. A minus a cancels out. Minus 8b minus 5b becomes minus 13b. Remember, we are subtracting equation number 1 minus equation number 2. So the signs in equation 2 will change. So this then, dividing both sides by negative 13, we then have our b as positive 6 out of 13. So that is b. Now that we have b, we can solve for a, the constant in that expression. Using either of these two equations, we can solve for a, which is only unknown as at this time. So I'll use equation number 1 to solve for a. So equation 1, now that b is known, becomes 4 is equal to a minus 8b, but b is 6 out of 13. Now this is the same as saying 4 is equal to a minus 8 times 6 is 48 out of 13. We multiply each side of this equation by 13 to get rid of or to determine a. So multiply the whole equation by 13 on the left, 13 times 4, and on the right, the whole thing. We multiply the whole thing by 13 so that we get rid of the improper fraction. This then gives us 12 carry 1, that's 52, 13a minus 48. 13a minus 48. Because 13 will cancel here, this would be 13, this would be 52. Solving for a, take the unknown to the left hand side of the equal sign. We have a minus 13a will be equal to minus 48 minus 52. So minus 13a is equal to, that is 52 plus 48. 10 carry 1, 9, 100, negative 100. So divide both sides by negative 13. You have our a as 100 over 13. So now that we have both b and a obtained, can get the equation. Substitute for a and b in the linear function. In the linear function, y is equal to a plus bx to get the actual equation that relates y and x. Doing that, we end up with the following. We then have y is equal to a, but a is 100 over 13. We had gotten b as 6 out of 13. If you may recall, so we have a plus b, 6 out of 13 times x. You can get rid of the improper fraction by multiplying each term there by 13. We have our equation of 13y is equal to 100 plus 6x, or 13y minus 6x is equal to 100. That's our linear function that goes through the points that are given in example number 2. Finally, still on constructing linear functions, we'll do another illustration in way of an example or a question, demonstrate how we can fix our a and b. The last example on the construction of linear function, or fixing the constants a and b in the linear function or equation as it were. Call it question number 3. Find the equation of the straight line whose slope is negative 5 and passes through the point, passes through the point 3, 3. 3, 3. Solution to this. Let the straight line equation be, let the straight line equation be y is equal to a plus bx as before, because this is a linear function. A straight line is simply a linear function or an equation. Now, we want to solve for a and b just like we did with the previous examples, so that we fix a relationship between y and x. Now, when b, the slope is -5, that is the slope, then this expression here becomes y is equal to a minus 2x. At the point x, 3, meaning when x is 3, y is 3, this expression here becomes the expression here, the linear equation here becomes, remember, x is 3 and y is 3. So substituting x and y in this expression, we have 3 is equal to a minus 2, another 3 because x is 3 here. We then have 3 a minus 6, meaning that which then means that a is going to be equal to 3 plus 6. When minus 6 goes to this other side, it becomes a positive 6. So we then have a is equal to 9. So at this point we have both the values of a and b. I think there's some correction here, beg your pardon. Correction, ladies and gentlemen. I'll repeat, just ignore what I've done. Now we were saying here when b is -5, this expression becomes, beg your pardon, that's a correction, we are correcting that. When b is -5 with the slope, b is -5, this expression becomes y is equal to a minus 5x, and not 2, because I'd put 2 here earlier, that was wrong. Then we proceed on from there. At the point 3, 3, meaning when x is 3, y is 3. This expression now becomes, remember, x is 3, y is 3. So this expression becomes 3 is equal to a minus 5 times 3. We have 3, a minus 15. So from here you can see that our a will be equal to 3 plus 15, which is 18. Not 8, but 18. So we now have the a and we have our b, so we can get the expression. So ultimately, therefore, hence, the equation of the linear, the equation of the straight line, is, substituting for a and b, that expression, we have y is equal to 18 minus 5x, because the slope was given as b. So that is the straight line equation that goes through the points 3, 3 with the slope of -5. Just some observations here. Way of presenting points. Observations. Presenting a point or points on an XY coordinate system. XY coordinate system. Observation: presenting a point on an XY coordinate system. In mathematics, we have various ways of presenting a point on an XY coordinate system. And this is what I was using in my 3 examples when we were constructing, or in the demonstration of the construction of straight lines. Now, one of those ways is simply writing the points in the following format. You can have them as x is given as a value, when x is 2, say for instance, y is 10. The second point, this is 1 Roman. When x is 5, comma, y could be something like possibly 8. So that's one way of presenting a point on a XY coordinate system. I simply write them as statements, the way I've put them there. The other way of formatting is in an ordered paired like version. Ordered paired like version. So like for instance, this is the first point. XY is equal to, say for instance, 3, 5. Ordered pair, meaning that when x is 3, y is 5. The second point will be something like possibly -4 and 12. That's another way of presenting a point on the XY coordinate system. It's the ordered pair approach. It is based on the concept of set theory, which we'll be doing later. The other aspect, you can present a point directly, like as follows: 3, 4, and 2, 2. That's ordered pair, whereby the first figure represents the variable x or x, and the second figure represents the variable y or the ordinate. Horizontal axis vis-a-vis ordinate. So that, ladies and gentlemen, is briefly how to construct linear functions. That's a very general approach. In real life situations, in applications, those must be translated in real life situations. So the next level, or our next subheading in the topic of linear functions, is going to be where do you apply linear functions, or application areas of linear functions in business and economics. So subheading, we are now on the applications of the expression I'd given us earlier. That is linear functions. So subheading here, where do we use linear functions in business and economics? So we'll tackle that as application of linear functions in business and economics. How do we use this notion of linear functions in real life situations? Now, when you talk of application of linear function in business economics, we are simply trying to see how this expression can be applied in real life situations. Where do we use it, and or what are those processes or scenarios that linear functions can be used in real life situations? So in summary, application areas includes the following. Number 1, in the area of computations of salaries and commissions for individuals. Salaries and commissions for individuals. Second area of application, bit of economics here, in the area of linear demand, supply, and equilibrium analysis. Linear demand, supply, and equilibrium analysis. The third area is the area of fixed asset accounting, strictly speaking, in the area of depreciation. Depreciation with the straight line method. Depreciation with the straight line method. Number 4, in the area of cost, volume, profit, and break-even analysis. Cost, volume, profit, and break-even analysis. Break-even analysis. Break-even analysis. So those are the 4 areas where the linear functions can be used to address problems that relate to the 4 areas I've just highlighted here. Now, when I say linear functions can be used in this area, this simply means that things like computation of salaries and commissions, you can use the linear equation to approximate an individual salary. You can also use the linear equation to determine the demand and supply functions. We can also use linear functions where we want to determine the value of a fixed asset or an item as a result of wear and tear, basically depreciation. And most importantly, for businesses, profit is the mainstay. The cost, volume, profit, break-even analysis. We have scenarios where the expressions on profit, cost, revenue, such expressions can be expressed by linear functions. For this morning or in this lecture, we shall deal with the first area, see how much I can cover in the time given, and then we can proceed on from there. The area of computations of salaries and commissions for individuals as the first area of application of the famous linear function. Computations of linear functions. Sorry, beg your pardon, students. Computations of salaries. Salaries and commissions. And commissions. And commissions. Now, generally, the total earnings for an individual comprises of 2 components. Individual's total salary and individual's total salary or earnings. Total salary or earnings comprises of 2 components. 2 components or 2 parts. 2 components or parts. These are: first component is the total fixed earnings or total fixed earnings. Fixed earnings. Example: individuals' basic monthly pay. Basic monthly pay. And the second component will be the total variable earnings. Total variable earnings, e.g. commission earned in total, or overtime paid. So those are the basic two components that make up an individual salary. There's that first component that is fixed or constant, and then second component which is variable depending on the sales volume, if it's a salesperson, or overtime paid if one has worked overtime. Now, it is evident therefore that an individual salary can be approximated or estimated by a linear function of the following form. It is evident therefore that an individual salary or total earnings can be estimated by a linear function of the following general form. That is, that function fits in an individual's total salary quite adequately. So where our Y here would represent the total earnings. Our A will represent the fixed earnings, total fixed earnings, a constant. Total fixed earnings, this is a constant. B will be the rate of commission if the individual is a salesperson, rate of commission, or rate per hour if the individual has worked overtime, rate per hour. X will be sales volume if the individual is a salesperson, sales volume in units, sales volume in units if the individual is a salesperson, for instance, or number of hours worked as overtime. Number of hours worked as overtime, And then finally, the product DX will stand for the total commission earned in total if the individual was a salesperson, or overtime paid if the individual worked in excess of the normal working hours. So you can see from this context that this expression here fits in an individual's total salary quite adequately, and consequently it can be used where it's required that one computes or determines the total salary for an individual. Right, like I was saying, you can see that this expression in the name of linear function describes somebody's salary or individual salary adequately, and consequently we can use it for all purposes where salaries, commissions, overtime paid are desired. This is because they are described quite adequately by linear functions, just like I've demonstrated here. Now, ladies and gentlemen, I'll be sending in advance handouts in form of illustrative questions or exercises, so that I don't keep writing my questions here. But for this morning, or for today rather, I'll design a question that will enable us have a feel on how a linear function can adequately be used in estimating an individual's total salary. Like I've said, I design a question that befits this area of salary computations. I'll call it illustration number 1. Illustration number 1. That's illustration number 1. Put it somewhere here. And I'm calling it linear function. Linear function in computing an individual's total earning and commission or overtime, whichever the case. So let me design and write the question on the board so that you're able to see them. We'll solve it together and see how this linear function adequately be used or can be used in computing salaries and commissions. A salesman's total daily earnings has two components. Fixed daily earnings and variable daily earnings, which is dependent on the number of ice cream units, sold per day, full stop. Now he finds that the salesman, that is, he finds that when he sells 10 units, when he sells 10 ice cream units, beg your pardon, when he sells 10 ice cream units, he earns 600 shillings. Whereas when he doubles his sales, the sales or his sales, comma, his total earnings increases by only 100 shillings, increases by only 100 shillings, full stop. Now that's the question regarding the salesperson. So I'll go to the requirements, the questions that we need to address in this problem. So required Part A, determine A. Part 1, his fixed daily earnings. His fixed daily earnings. Part 2, his rate of commission. His rate of commission. Rate of commission, that is, how much does he earn per one ice cream unit he sells or sold. 3, his total earnings. His total earnings. His total earnings when on a particular day, when on a day he sells 30 ice cream units. 30 ice cream units. Part B. Part B of the question. The salesman is determined. Salesman is determined to earn a total daily earning. A total daily earning. Total daily earning of 3,500 shillings. How much more? How many more? Beg your pardon. How many more ice cream units? How many more ice cream units ought he to sell? Ought he to sell if he had a guarantee of 20 ice cream units. 20 ice cream units on the previous day. On the previous day. On the previous day. What I mean here is, if you had a guarantee of 20 units previously and he needs a target of 3,500, how much more should he add on the 20 so that he's able to meet his target earning of 3,500 shillings? Now here is the solution. Here is the solution to the same. Now, right from the outset, we are told that his total earnings has two components, fixed and variable. From that statement, it's evident that we can actually estimate the salesman's total daily earnings by means of a linear function. So since total earnings for this total daily earnings for the salesperson has two components. We may use the linear function. Y is equal to A, B, X to compute the salesman's earnings. Y is A plus BX. This is because it approximates the daily earnings of the salesman adequately. Look, Y is his total daily earnings. A would be representing his fixed daily earnings. B, rate of commission in this case, it will be number of ice cream units he sells. Sorry, how much he earns per ice cream unit sold. X being the total number of ice cream units. Let me just write this for us so that you're able to remember. So Y is the total daily earning. Is total daily earnings. A, fixed daily earnings, a constant fixed daily earning. That's a constant. B, this time round, rate of commission, how much he earns for each ice cream unit he sells. X, number of ice cream units he sells, number of ice cream units sold. Alafu the BX with the commission earned, total commission earned, commission earned. So you can see that that expression describes his salary adequately on a daily basis. Right, the information I gave us will be able to fix A and B. We are told that when the salesman sells 10 units on a given day, his total earnings are 600. That's like 1 point. So this expression becomes 600 is equal to A plus 10B. Similarly, when he doubles his sales, doubling means twice what he sold previously. So from 10 to 20, his total earnings increases by only 100. So this expression becomes 700 is equal to A plus 20B. Remember, he doubles his sales. If previously it was 10, that's 10 times 2, we have 20 there. So those are the expressions. We solve for A and B like we did in my general examples. By elimination, subtract equation number 1 minus 2, you come up with 1. Negative 100, A will cancel, so we have a minus 10B. Divide both sides by negative 10, you can see that the B is going to be 10. We can then, using that, get the value for A. You can use any of these equations to get your A. If I take the first equation, which is 600 is equal to A plus 10B. But our B is 10, so we have 600 is equal to A plus 100. You can see that A is going to be 600 minus 100. We end up with 500. We then have A and B, so hence his total daily earnings becomes Y 500 plus 10x. That's the equation or the linear function that describes the salesman's daily earnings. Now with this, we can then comfortably answer our question. Part 1 of A. Part 1 of A, we want to determine his fixed daily earnings. From what you've just established here, A was a fixed daily, it is 500 shillings. So daily earnings, fixed, which is constant here, for this salesperson, it's our A, and that is simply 500 shillings. Part 2, the level of commission, rate of commission, how much does he earn per unit of ice cream sold? That is our B, the slope mathematically, but yet is the rate of commission. So rate of commission for the salesperson, that is the B, is 10 shillings, meaning that for each ice cream unit he sells, he earns 10 shillings. Part 3 of A, The total daily earnings if the salesman happened to have sold 30 units on a particular day. That simply says that when X is 30, then we have his total daily earnings. Just substitute for X in the expression for his total earnings here. Substitute for X here, you'll get the following. Y is equal to 500 plus 10 times 30. That is 500 plus 300, and you can see that Y is 800. So his total daily earning, if he sells 30, is 800 shillings. So earnings, total daily earnings. Accuser 300, rather, if he sells 30 units on a given day. So his total daily earnings is simply 800 shillings, 800 Kenya shillings, or whatever that one is. Yeah, we still have a part B, but we can pick that one in the next lecture. So thanks very much, ladies and gentlemen. See you the next, we continue from that point where I've stopped.